Good afternoon, everyone. Welcome to the session Networking Architecture this afternoon. Our first presenter will be Rob Evans, who is currently Chief Technical Advisor at Janet and co-chairing the RIPE Routing Working Group. He held various positions in several projects at Janet, Imperial College, ULCC before, and he is working on networking since the period of 10155. Rob is now the leading architecture designer of the Janet 6, and his presentation he will give some insights what the NREN should look like from his perspective. Rob, please give your presentation.
Yeah.
Thank you.
Thank you, Janusz. Well, hello. As Janusz said, I'm Rob Evans. I'm the Chief Network Architect of Janet. Just noticed there's a little Apple TV box on the table here, so bonus points for anyone that can get Game of Thrones to stream instead of my slides. So it's called Building the Perfect NREN, and I guess the first place to start with this is what do I mean by perfect? If you're building an NREN, is the perfect NREN one that's based on all the user requirements now and for the foreseeable future? Is it an ideal network? Is it a network built without making any compromises? Is it a network that achieves the right balance between cost, management, features? What's meant by the perfect NREN? Perfect in the dictionary on my Mac is described as having all the required or desirable elements, qualities, or characteristics, as good as it is possible to be. So it's really balancing everything. It's getting a network that solves all the problems that you feel you need to solve to serve all the functions it needs to do. Plus, of course, it has to be affordable. It has to be something that you can realistically build. So we've just finished the build of Janet 6, and I'm not going to talk much about it. It was a long process. We started off with a bunch of requirements gathering workshops from our more demanding users, from the FE colleges, from people that require nothing more than the internet as a day-to-day commodity, through to the particle physicists, the bioinformatics people, those that need the really cutting-edge features on the network. Along with that, there's a whole bunch of capacity planning, usual sort of thing of drawing graphs that go up and to the right for the number of bits per second you have to shift. There was a whole stream of government engagement to make sure that we could get the funding for it, and that in itself was a lengthy process. There was the procurement process itself. I'm sure I don't need to talk to any of you about the competitive dialogue process. We had multiple providers for fibre, multiple providers for optical equipment, 3 or 4 rounds with each of 6 vendors in each of those was a major sap on time. Then there's actually building the network and migrating to it. And what we ended up with was a dark fibre network across the UK with a coherent optical system on top of it, lots of 100 gig 2800 gig circuits on day one. Ethernet over MPLS to provide some layer 2 circuit capability. We don't have OTN switching, and I'm not going to claim it's the perfect NREN, but I think it's a pretty good NREN. So, what's the perfect NREN? Well, one of the main things all of the users want is high capacity IP provisioning. It's the fundamental component of the NREN. It's flexible. By its nature, it's statistically multiplexed, so it copes with peaks, as long as you provision sufficient capacity, it copes with peaks in demands. Because you have a large user base, it averages them out between the demanding users, between the demanding media events. Then there's the ability to rapidly provision circuits, layer 2 circuits. There's a large demand for these, light paths, GR+, whatever you want to call them. No, that's not necessarily guaranteed bandwidth, but not congested. Then there's rapid provision of dedicated bandwidth, whether that's the megabits per second or gigabits per second at the lower end, or the many gigabits per second for the high capacity data transfers. Of course, it needs to be reliable, and that's reliable in the face of multiple failures. And then there's the balance between the production network requirements, which serves 99% of the users, and the network research, the other 1% or half of 1% that want to try experimenting with the network, which of course mustn't impact the production network. So basically, I want a unicorn. How might that network be built? Well, the layers, the standard ISO layer model, dark fiber, layer 0, optical layer on top of that, a switch layer on top of that, a routed layer, then your network management, the software that controls how you're going to build new bandwidth, do automated provision, and maybe some degree of network intelligence. And over the rest of the presentation, I'm going to cover each of those in a bit more detail. So, dark fiber. Do you need it? Well, dark fiber, as we all know, is good for high capacity, and it gives you good visibility of the underlying network. And by that, I don't just mean faults on the fiber. I mean, if you're operating a dark fiber network, then you have the knowledge about what the fiber is under the network. You know whether any new technologies are going to be ones that you can deploy because you know the underlying characteristics. You know the capacity that you have left. You know how close you are operating. But it requires a long-term contract. Janet 6 was the first opportunity Janet has had in it, and we're celebrating our 30th birthday this year. This was the first opportunity we'd had to buy a dark fiber network. Because the funding cycles being short-term, 5 to 7 years, made it very difficult to commit for a dark fiber network. With circuits, allow a telco to share the fiber between you and others. So if you don't need the capacity, then maybe it might be a cheaper option. And maybe there's a third way in the middle, maybe sharing part of the optical spectrum. There are some telcos that will do this in the UK, and I think there are others that might do it, spectrum sharing things on transatlantic or transoceanic fibers. One of the other problems with dark fiber is, can you get it? In the UK, the fiber market is fairly limited. At the end of our dialogue process, we only really had 2 people coming forward and offering us a nationwide dark fiber network. The fiber glut of the early 2000s is history. The telcos today want to sell more services over the existing fiber rather than lay new fiber. Laying fiber is expensive. And that leads on to, will you always be able to get it in the future? So unless new fiber is laid, the market is not going to open up. And even if you build a dark fiber network now, will you be able to expand it in 5 years' time, in 7 years' time, in 10 years' time? And how much fiber do you need? How much of a mesh do you need? Many routes around the country may create a resilient network, but how are you going to utilize those routes? How many degrees are you going to require on your optical nodes? How are you going to use that fiber? Are you going to use switching and protection at the optical layer to route traffic around these many paths? Or are you going to statically provision IP paths over all the directions and then have the routers handle the rerouting? That means lots of router ports, expensive router ports, and a complex IGP topology. So simpler may be better. It's a matter of finding the right balance between the fiber that's available, the mesh that you might require, and what you can afford in terms of having a resilient network, a network resilient to several failures. Then, what do you put on top of that? Well, how reconfigurable do your ROADMs need to be? With ROADMs, less is more, as in colorless, directionless, contentionless. The more of those you have, the better ROADM it is, apparently. And that's going to be based around your capacity planning. Capacity planning and traffic planning for the network are the key things for how you design it. Do you need colorless? Do you need directionless? Do you need contentionless? If you're going to be using a large number of channels on a network, then the chances are you're going to need more of those features to be able to avoid having to go from the optical domain back into the electronic domain to go back into the optical domain to go onto a different lambda elsewhere in the network. Are you going to want to be able to dynamically reroute some wavelengths around the network? So are you going to want to build networks that go from arbitrary directions from any particular node? In case of a failure, are you going to want to reroute them? I'll come to that later. On your ROADMs, what sort of WSS do you want? A MEMS WSS is the kind of de facto standard really at the moment. It's the current technology, but it operates with fixed 50 gigahertz grid slots. Future technologies might be using LCOS, the liquid crystal on silicon processors, which enables the flexi-grid technologies that allow a more dynamic and more approach to bandwidth allocations. So I mentioned briefly the rerouting wavelengths. If you're protecting the optical circuits, then you can either do that statically. The processors aren't the sort of technology you want to be using for rerouting the circuits instantly. It takes a few seconds for MEMS to flick a wavelength from one direction to another direction. Then do you go coherent? I know during the design of Giant 6, I know during the design of GN3+, whether to go coherent or not was a fairly long topic of conversation. Because the implication is if you're going coherent, you aren't having dispersion compensation built into the network. So with coherent, you can drive 40 gig and 100 gig over huge long distances. But doing the 10 gigs then, doing the simple on-off keyed 10 gig circuits across an uncompensated network is expensive. It's not impossible, but it's disproportionately expensive from doing it over a network with dispersion compensation in. So it's coming back to your capacity planning, your traffic matrix, where you expect the network to be, the traffic to be going on the network. And then there's, do you have a thick optical layer and a thin routed layer, or a thin optical layer and a thicker routed layer? So this was something we'd hoped to be able to exercise a bit more during the Giant 6 procurement, really. The standard architecture is that you have grey light optics in your routers. They connect to a transponder in the optical equipment that then sends out a long-haul WDM signal. The other alternative is that you have OTN optics, coloured optics in the routers. But the problem with that is that they're still several years behind the optical vendors. The router guys are just, the coherent requires a lot of digital signal processing, and fitting all that as well as all the general router stuff, so the packet buffers, the forwarding engine onto the router, means that they're still a fair way behind. And so when we're doing Giant 6, WDM 100 gig optics for routers was still a few years away. And even then, the 10 gig ones are only really starting to come into availability. Now, there's some very early soundings of some 100 gig WDM OTN optics available in, say, Juniper MXs, but it's still a few years behind the dedicated transmission vendors. Of course, the counterpoint of that is you have to pay the penalty of grey light optics and your OEO. So on any signal path, you've got the grey light optic in the router, the grey light optic in the transmission equipment, the WDM optic, and then the same at the other side. And when 100 gig optics are expensive, and 100 gigabase LR4 is very expensive, then you're paying a lot of money for sending a signal a very short distance. And the other major discussion topic is the switch layer. What's switch layer? Where do you put the switch layer? So what do I mean by switch layer? Well, it's basically something, some glue between the optical layer and the IP layer. Circuits, in other words. In the X25 days we had them and binned them. In the 18M days we had them and binned them. It's things that we're going to reinvent whichever layer of the network technology we have. So what will you be using the switching layer to provide? Dedicated capacity circuits, okay. Low capacity, high capacity, that's going to affect where you put them. Is it going to be the underlying packet, such as the multiplex aggregation layer of your network, or are you going to be building that on top of the IP layer? Is this going to be where you build your pool of bandwidth, or are you going to be building a pool of bandwidth here and a pool of bandwidth at the IP layer, which means more overhead? So where should it be? If you put it in the ROADMs, you have OTN options, you have Ethernet options, you have dedicated boxes that can do the switching. Of course, more boxes means more rack space and more power. You can do it in the routers, using Ethernet over MPLS. But to go back to the point I was making at the end of the last slide, the more places you build in switching capacity with the idea that you're going to be able to build circuits on demand, then the more places you're going to have to build dedicated pre-provisioned capacity before you actually need it. And then the next level up in the stack, the IP layer. How many backbone routers do you want? the CTO of Janet, Bob Day, is always asking me how many routers do I want, and I always say twice as many as he let me buy. So you don't obviously want to carry traffic further than is necessary. You want to be able to have some sort of routing switching layer that can route the traffic relatively close to the source and destination. But equally, you don't want to be overdoing that. The router ports are expensive, and you don't want to process the packet at many hops along the way. So it needs to be a compromise, again, between the number of routers, the traffic patterns, and possibly some, if you've got large flows going places, maybe offloading them onto dedicated lambdas. How far do you manage them? I've got this as a bit of a futures thing at the moment. I mean, I say futures, I mean, Dave will know more about this. If you're managing CEs as well, do you have any option to collapse the C and the P using some, network function virtualization is the acronym du jour. And of course, on the IP layer, I'm going to say V6 just because I always say V6, and you are all doing V6, aren't you? Scaling the IP layer, that's again a major overhead for us, a major headache for us, I should say. Power and space. We have Juniper T4000 routers at the moment, and the switching capacity of the routers always seems to be lagging a little bit behind the growth of the packet switching that we're actually using. We kind of asked the vendors, please, make a denser router that takes less power. Let's go back to this unicorn I want. But they always say that, well, we can't really do that. What you need is more boxes. But of course, more boxes is more expensive. It's more rack space, and it's more power, and it's more air conditioning. Telehousing for us is not cheap. We go into somewhere, we want to put the T4000 in, we say it takes up to 12 kilowatts of power, and they say, fine, buy these 3 racks and put 1 box in one of them. So scaling the routing plane is one challenge. Then 100 gig is a lot of traffic. When you're building a network, 100 gig is a big chunk of traffic that you have to fail over to one way or the other, which means you having to build a lot of 100 gig circuits to back up the capacity. And 100 gig base LR4 optics are still very expensive, but they're easier to manage. They use single mode normal patch cords. 100 G base SR10 are cheaper, but they require special cabling, the multi-core, multi-mode cables with these MPO connectors. 10 by 10 MSA is a nice option. It uses normal single mode fiber, but is closer to the SR10 price than the LR4 price, but very few vendors actually officially support them, which is an issue for us because we don't have a large staff to go around the country and manage the optics ourselves. We rely on the vendor support. For us, when we designed Janet 6, the price saving across the network for SR10 rather than LR4 was somewhere in the region of £1 million, so 1.2 million euros. So we ended up with using SR10. One of the other options maybe is to stick with parallel 10 gig E. That limits you, of course, to having no single flow larger than 10 gig, and it requires lots of cabling. And it also means that if you require all of the capacity in a bundle, then you're reliant on all of the optics. So if you have 10 links in that bundle, then you're now relying, instead of 2 optics, you're relying on 20 optics. And so you've got to bear in mind the failure modes there. Cause. Now, this is something that keeps coming up again. This is a quote I actually took from a paper yesterday I think it was on a discussion forum on LinkedIn. Owen DeLong, you don't need quads if you build an adequate network. This is still our stance on Janet, really, because if you're preferring some traffic, that means you're prioritizing it over other traffic in some scenarios. And how do you do that admission control fairly so that it's only the VoIP traffic that's prioritized, but equally it's open to and equitable to all VoIP providers? We've had some of the sites on Janet have really asked us about quads and are starting to really press us quite hard on quads. It's something that we're going to be looking at again. I'm interested to know what other NRENs are doing with quads. Are they prioritizing VoIP traffic in some way or another, and how are they doing the admission control? Because there are circumstances where it might be useful. For example, suppose a site is, one of our customers is now using a fully outsourced phone system, but they come under a DOS attack. Now, if we're prioritizing quads, their phones might keep working, whereas what they're telling us is if we don't prioritize quads, not only does their network stop working, but their phones stop working. And part of the design of the scaling of the IP layer is how you build content delivery. For us, and I'm sure for many other NRENs, lots of our traffic comes from the usual sources. The Googles of this world, the Akamais, the Limelights, the Netflixes. And there's a couple of options here. One of them is the house servers. I mean, Netflix can serve several gigaseconds from a 1 rack unit, 300-watt server. And so you can, bung those around the network, distribute those around the network to reduce carrying traffic around the network. But then you have to pay for the power, the rack space, the time spent arranging for broken servers to be replaced. And if you've got a Google server somewhere, does that mean you also need an Akamai server and a Limelight server and a Netflix server? And what about the next big CDN? We're quite lucky being in the UK that we can just peer. There are a lot of all the major content providers have some really good peering ability in London and increasingly in Manchester, so we can actually peer in 2 locations on the network and spread the traffic about. But I'm fully aware that's not available on all locations. And even if you can peer in one place, that doesn't mean you can peer in many places, so you might need to carry the traffic around the network. So it's not, sometimes it's easy to add new peers, sometimes it's not. And cloud access. With a lot more outsourced services, you need to bear in mind the ability to get close to Google, to Microsoft for Office 365. So, coming back to the rapid provisioning, if you want to be able to write capacity at a moment's notice, then it needs to be sitting there unused. That's expensive. It may never be used. And finding the money to build all this capacity on the off chance that it might be used at some point is expensive. And the technology may be obsolete before it actually is used. Future technologies like FlexiGrid and dynamic encoding, where you can literally ramp up the capacity of a single wavelength, hopefully going to help a lot here. But with the current sort of, even with most dynamic networks at the moment, building high bandwidth is still going to be something that requires a bit of a lead time. Automated provisioning. Well, first of all, know what you're setting. Are you really setting bandwidth on demand, or are you setting a circuit on demand? Lots of bandwidth on demand at the moment is really just a layer 2 point-to-point circuit. And there are several ways of doing that. Things like Autobahn, as long as you write the technology proxies, and it's really good for an interoperable solution. But equally, then you might have vendor-specific solutions, which are really awkward if you have, our network, I know, has got a bunch of Junipers, a bunch of Ciscos, there's probably some other odd boxes lying about. And so when you start building these tools, how much experience of the network operations does your development team have? And what they're doing, is what they're doing going to tie you down in the future? I mean, do they understand what they're actually building, or are they building to a set specification which is going to make it restrict what you're doing in the future? And the big thing with automated provision, of course, is who's actually the user. How do we get to the end user? How do we authorize the end users for proper bandwidth on demand, or at least layer 2 circuits on demand? Network intelligence. How smart should a network be? Historically, networks have been fairly resilient because they've had distributed control planes through BGP, OSPF, ISIS, LDP for the MPLS. There's a move now towards centralized control. SDN, of course, being the canonical example, but also MPLS-T using centralized software to provision and route LSPs. Is this a good thing? Do you trust the smart things in your network? Do you trust the Robbie the robot sitting there typing in the commands? So there's obviously a balance. You need networks can no longer be these statically built things that you design once and are left there to sit for 5 years. There needs to be a lot more adaptability to come into them to serve people's needs, but how do you do that? Network monitoring, I'm getting towards the end now, so my time is running up. Now that you've got your dark fiber, your optical layer, your switch layer, your routed layer, and your automated circuit provisioning, how do you see what's going on between all those layers? You might have your Sienna or your Adva or your Altair Lucent optical monitoring tool. You may have your OpenView or your Nagios looking at the IP layer. You may have Autobahn sitting on top of those building the circuits. How do you provide a way for your NOC to easily see what's going on in the network? There's a couple of options here, of course. You've got your expensive commercial tool, which does it do what you want it to do, and how much does it cost to change it? Or you have open source alternatives. We're building one at the moment that's hopefully going to talk to both our IP layer and our optical layer. But it does require quite a bit of investment of time and effort. And it will require some interface modules to talk to, say, certainly the optical layer. There are a couple of options for our Sienna stuff, for example, one of which is called TMF814, and the other one is, acronym I've forgotten now, MTOSI. The MTOSI one was prohibitively expensive. TMF814 wasn't so expensive, but it doesn't quite do all we want, and it requires you to become a member of the TMF to actually get the interface modules off them to fit into the Sienna stuff. I mean, so this has really been a kind of quick gallop through some of the things that you need to think about when you're designing an NREN. What is meant by the perfect NREN is obviously going to depend on what your users are, what your users' demands are, and what the requirements are, and what's available to you. So with that, I think we might have a couple of minutes for some questions and discussion.
Thank you very much for your presentation. Any question from the audience? If not, I have a question. Okay. What do you think of the Y generation? The Y generation is prefer using mobile phones. How could you consider integrating their requirements into the perfect NRN scenario?
Good question. And when I say good question, it usually means one I'm not sure how to answer. It's the seamless wireless stuff is, for quite a few TNCs and quite a few years in this environment, there's been this phrase, martini networking. I don't actually like the phrase because to me it talks about point-to-point LSPs and a draft dash martini dash blah. But the theory being anytime, anywhere, any place. And what we've done in the UK is partner with a bunch of mobile providers, or a few mobile providers, and try to arrange overlays on their networks that give them a direct access back into Janet from that. So kind of win-win situation. So you can be on Janet. You have access to Janet resources even though you're using your mobile phone. On mobile, not just on the Eduroam Everywhere Wi-Fi. Doing it from home, using static DSL cable, whatever. I think partly that boils down to having good interconnects. Part of the theme of the conference is networking with the world. So NRENs can't live in isolation. They have to work with the environment around them, with the service providers around them, to network with the world. And so you have to have the good peering arrangements, and you have to get away from the mindset of an IP address is an identifier for a big one. You have to be able to authenticate, build in authentication systems that's based around who you are rather than where you are.
Okay, thank you very much. So thank you for, okay.
Sorry, that was a bit last minute, wasn't it? Hi, David Wild from ARNet in Australia. One of the trends that we're noticing is that the network is not enough. You need to be, our customers and we and commercial providers are adding compute and storage and tying that to the network and then layering applications on top of that. Do you see that as a, when you talk about the perfect NREN, do you see that as an additional trend or a direction that Janet's being pulled in? And how does that alter your network architecture kind of design work?
Yeah, that, again, I really glossed over this. I probably tried to cover too much. The cloud access, the peering side of this is getting access to these services, the things that other people the services that people are building. So there's the bits and bytes. There's the shipping traffic from the cloud service provider to the user. There's the authentication layer. We haven't seen so many demands for much different in terms of network services, in terms of point-to-point circuits or service on demand. Maybe Amazon Web Services is the only one of those instances so far. Yeah, Amazon Direct Connect, sorry, is probably the only one of those so far. So it's still kind of emerging, in my opinion. A lot of the work that the first guys to do, I suppose, is to work on the trust aspect, to work on the dealing with the providers, to know where the data is going to be held, how it's going to be, how it's going to be accessed, linking the identity systems into it. But I think on a network level, as I say, so far we haven't really seen much of a demand other than shipping a large amount of data, but shipping packets is what we actually can do quite well. It's the more complex things on top of that, the trust and identity things that are where the work is at the moment, I think.
Okay, thank you very much for your presentation and your talks. Unfortunately, so our next presenter will be Gianluca Reali, who is associate professor at University of Perugia. He was a researcher at University of Perugia and Computer Science Department of University of California, Los Angeles. He is member of editorial board of IEEE Communication Letters. He is currently coordinating several national and international activity at the University of Perugia. And he will present what are the researcher needs in a research network perspective, especially in the RS project, Advanced Networking for Distributing Genomic Data. So, Gianluca, please give your presentation.
Thank you, and good afternoon to everybody. I'm glad to show you the currently available achievements of the project RS. RS is a project accepted in the framework of the first GEAN open call. And during my presentation, I will give first a general description of the project. Then I will show the main research issues and implementation issues. Quite a long phase of the project has been devoted to implementation. Again, the technologies that we have used in our system, and something about the design that has led to the implementation. The presentation will go on with the status of the project and some experimental results that we have achieved so far. So, as I mentioned before, RS has been accepted in the context of the first GEAN open call. Essentially, the aim of the project is to find the best practices and implement them for managing genome datasets in the network. This project includes two partners, the University of Perugia, the university I come from. We have to handle anything about networking, implementation, and research in networking. And our companion partner is a research center on genomics, genetics, and biology. And they have to support us with all the issues related to the use of genomes for medical and research purposes. So it is commonly believed that in a few years, a lot of individuals, most of individuals will be sequenced. The size of a human genome is about 3.2 gigabytes. This is just the size of the genome, but all annotations, all auxiliary files that are needed for using a genome file can reach the size of tens of gigabytes. So it is a huge problem. Also because the price for sequencing a human genome is decreasing faster than the Moore's law. For this reason, it is believed that in a few years, the real bottleneck for the widespread diffusion of genomes for medical purposes will be the network. Currently, the greatest center for sequencing center in the world is located in China, in Beijing, and currently they send the result of their activity by sending hard disks through courier mail. So it is a real big problem, a big issue. It is necessary to find a suitable network architecture to handle them. It is clearly necessary, needed a lot of capacity, but also a network architecture is important for exploiting the network resources at the best for handling genomes, human genomes. Well, this picture shows the main actors involved in the RS system. We can see the medical centers and research centers, distributed databases storing virtual machines. Well, virtualization is a key component of the RS architecture. Virtual machines are available in the network in some databases, but not only virtual machines, also genomic datasets, human genomes, and relevant files used supporting genomic processing, auxiliary files. Here we can see an entity, the genome CDN manager. I will show later on the key role of this entity. And essentially, the access to services are managed through a cloud interface. And at the end of the game, the answer is given back to the requesting medical personnel in the way I will show you in a few minutes. Well, one may think that a genome file is just a file. It's a larger file, but just a file, and it is possible to handle it likewise any other file in the network. It is possible to do that, but it would be highly inefficient due to a lot of peculiarities of genome datasets. These peculiarities consist of the content growth, the content popularity, and the logical relationships between genomic files, between diseases having genes in common. I will say something on these peculiarities in the next slides. We have addressed the problem through addressing these issues: content distribution logic, suitable content distribution logic, integration of cloud storage and processing services, a novel cache instantiation procedure that we have implemented, an optimized downloading, and other things that I will show you step by step. Oh, sorry. This is remote. Good. This snapshot is taken from the portal 1000 Genomes. This portal makes available human genomes, polished, freely usable for research purposes without having to handle with privacy issues. I want to just show you that for just 1,000 samples, the storage space needed is more than 400 terabytes for just 1,000 samples. Imagine what could happen if a major city in Europe or worldwide will have most of the people sequenced, the really huge problem to be handled. And we started from this consideration. Well, for what concerns the size of the files, we just make a simple comparison of a genome dataset with a typical content in the network, in the internet. For instance, a movie. The size of a movie is clearly constant over time. Constant over time, regardless the use of the movie. But for what concerns a genome content, a human genome is still a huge amount of unveiled information. And once a given genome content is made available in the network, all processing, all research activities, all medical activities over this content makes the aggregate data set growing over time, increasing over time, and this is a major challenge for the network, for handling the storage in the network. Again, for what concerns the popularity of the content, let's go on using the movie as a comparison. Clearly, once the movie is made available, after some time, sometimes there is a peak of popularity, then the popularity vanishes over time. It happens commonly for most of contents in the internet and in network in general. But for what concerns the genome contents, the situation is very different because it happens sometimes that a very old genome is interesting for research and medical issues much more than a very recently sequenced genome of healthy people, for a healthy person. And what happens in terms of popularity is totally unpredictable over time. And this is another challenge for managing these contents and exchanging contents in the network. Again, another information is related to the link between genetic link between diseases discovered in the medical research, by the medical research. This is a snapshot taken from the portal diseasome.com. And they actually map all human diseases. This is the higher layer view of the map. And in this picture, each circle is associated with a disease. The size of the circle is associated with the number of genes involved in the disease. And an arc means that between two diseases, there are some genes in common. From the networking perspective, this means that if, for instance, a diagnosis of leukemia is done, it probably will triggers another analysis for colon cancer because they are highly connected. And from the networking perspective, this may use pre-caching contents so as to answer to serve the medical request in a shorter time. So this is a peculiarity that is present, is offered only by genome's dataset. Well, for what concerns the distribution logic, it is based on ANSYS. I'm pretty sure that most of you already know ANSYS as a signaling platform developed in the framework of IETF, the Internet Engineering Task Force. Again, we aim at providing differentiated services, network services according to differentiated medical needs. Access to services will be orchestrated through a cloud interfaces implemented through OpenStack. And another important component that I will describe later on is the middleware NetServe. NetServe has been implemented by the University of Perugia in collaboration with the Columbia University of New York in the framework of a project funded by the US NSF. And this middleware is a key component of the ARES experiments. Well, this is the description, an illustration of ANSYS. It is made of 2 layers. The top layer, NSRP, the ANSYS Transport Layer Protocol, implements the signaling application, satisfying the need of the RS services targeted for genomes. The lower layer provides the mechanism for transporting, signaling, and it makes use of the most common transport protocols such as TCP and UDP and SCTP. And a fundamental component of this layer is GIST, General Internet Signaling Transport, which has been defined by IETF again. For our experiments, we made use of an implementation of GIST provided by the Karlsruhe Institute, Karlsruhe Polytechnic Institute in Germany. And we have modified this signaling, this component, by introducing off-path signaling. Essentially, we have modified ANSYS in order to disseminate the signaling around the transmitter balloon, around the receiver, about the transmitter bubble, about the receiver balloon, or within a pipe close to the path connecting transmitter to receiver. This is referred to as hose. Well, this is the architecture of NetServe. You can see here that ANSYS is a key component of NetServe. The current implementation makes use of a Linux kernel, and all actions here are orchestrated by the NetServe controller, which is a C++ implemented components, which orchestrate the instantiation of services. Services are implemented as Java bundles organized through OSGI components. And we actually have an activity, an ongoing activity, for implementing this transport over the Juniper operating system. And we hope that by the end of the project, that will be in March 2015, we will have also a version available for giant routers executing Juniper operating system. Well, here in this figure, we show the POP organization. The cloud interface is managed by OpenStack. We made use of most of OpenStack components. OpenStack is an open source software for managing cloud access to available resources. And we used all the main components, such as Nova for managing virtual machines, Glance for storing virtual machines, Neutron for network configuration and management, Keystone for authentication, essentially all needed things for providing a service in operation. And in addition, OpenStack also managed the instantiation of NetServe middleware in virtual machines. So from the user perspective, through the use of OpenStack, it is possible to access services just as a typical cloud interface without having the need of handling the complexity of a content distribution network. So here, this figure, we represented the signaling exchange, making all the system working. Everything starts with, sorry, I have to change the remote. Everything starts with a request from made by medical personnel from a web interface. This request is issued to GCM, Genomic CDN Manager, which is the brain of the system I have introduced before. Here, each red box means a NetServe bundle. So we can see here all the components implemented within NetServe. After the GCM has been contacted, the genomic CDN managers queries the database management system just to be informed about the location of the repositories where virtual machines for processing genomes and genomic datasets are available in the network. After this information is returned, an NREN signaling session starts. I will show you then what is done in these yellow boxes. And during this signaling, all nodes connecting repositories are checked in order to verify if available desired contents are available as are already available in caches. During the signaling, also an optimization function identifies the suitable location where the processing has to take place. Then, at this point, the CDN instructs the selected POP to retrieve all components, all the software and genomic datasets through other ANSYS signaling phases. And during these phases, a lot of mirrors in the network are loaded with data coming from repositories in order to make this data available for future requests. Then, when all data are gathered within the selected POP, the genome processing takes place and the results are returned back to the medical personnel. So from this point to this point, the access is very simple for medical and personnel and research personnel. RS consists of this exchange and processing beneath. And just to understand exactly what's going on, I have to show you here what happens in these yellow boxes. Essentially, the first step that trigger an ANSYS signaling is an HTTP request, an HTTP GET from the client to the HTTP server. At this point, the first exchange, the setup exchange, is used to trigger, to instantiate mirrors in nodes along the path connecting the server to the client. Then the probe exchange, the next phase, is used to make the server aware of ANSYS nodes in the path to the client, towards the client. The third step, third signaling, is used for associating each node in the path to the upstream node. So we have, in this way, realized a chain from the client to the server. So remember that the first step was an HTTP GET. Then, when an answer is returned back to the client, this answer is a redirection to the upstream node to the client. In turn, the HTTP GET is issued to N1 until this request reaches the server. Then, when the server sends data, the data are stored in caches along the path, and all genomic contents of virtual machines are made available in all nodes in the path. This means that when a subsequent request will be done, data are made available without any further exchange, and the result is a real advantage in saving resources in the network when the number of genomic processing requests is very large. So, well, everything works well if a suitable optimization function for determining the suitable POP for executing genomic processing is in place. We have developed such a function. It is the result of a huge mathematical activity. Now we are in the process of integrating this function in the Genomic CDN manager. Essentially, this function has to take care of the type of request issued, the size of the files to be handled, metadata size and location, virtual machine size, network topology, clearly, bandwidth of links, the service time required by the medical personnel according to the seriousness of the disease to be handled, and the reliability of the results desired by medical personnel. And in some instances, we also make use of parallel downloading, because we have also developed a protocol for determining disjoint path in the network in order to make the downloading as fast as possible for situations very, very serious. Well, this is just an arbitrary classification of the CDN services that we have developed. Clearly, the first category is the category of very serious situations that to be handled in a very short time. The last category is the category where it is not very important to provide the results in a very short time, but we can also handle network resources so as to maximize the number of analysis that can be executed in a given time frame, 5 minutes. Okay. This table just is provided to us by our partner in the project, shows the time needed to have a diagnosis, to have a result of the processing. Well, some days could seem a very large time because the processing takes some hours typically, but for a single service. But if thousands of services are requested, also this time frame is really challenging because of the size of genomes, auxiliary files, and the heaviness of the processing. This slide shows 2 case studies that we have implemented, copy number variation and differential expression. They are genomic pipelines. Please don't ask me details about the single component because it's not my subject. What I can say you here that each component is open source, and these pipelines are very used, frequently used for medical purposes and research purposes. Are very frequently used, and they have been actually implemented in our system, and they can be executed in our trials. This table shows the minimal resource requirement for some case studies. A few time, it is necessary in a case to focus on this column. This column shows the storage space needed, the minimal storage space needed for each pipeline in the different configuration. So you can see here that numbers are quite high, and from the network perspective and the processing perspective, it is quite huge to implement this kind of service in a network, also in a wideband network. Some experimental results. In this figure, we have the processing time of a single pipeline versus the number of cores. You can see here that increasing the number of cores in the pipeline gives a relative advantage. So a trade-off between performance, processing time versus the number of cores can be implemented, can be done. Different curves are relevant to different amount of RAM associated to virtual machines, and we can see here that the amount of RAM, once the minimal quantity has been allocated, is not a good trade for improving network performance. Just a figure to show how resources are used over time. There are some steps in which all the resources are used, and sometimes where just a few resources are used. This is just to say that an aggressive multiplexing can be done to maximize the number of processings in the network. Well, we had not the opportunity so far to use a real network, just we use the network in our lab. We hope in the next future to make use of some giant resources. But in the meantime, just to have a preliminary evaluation of achievable performance, we have represented the giant network in a simulator, in a co-level simulator, emulating all links of the giant network, and we have executed some experiments just to have some expectations of our system in terms of usage of network resources. Here we show the setup of the simulation. It will be too long, maybe now, to describe everything in detail. Just to say that requests are assumed to be to arrive to the GCM according to a Poisson process. Users are assumed to be uniformly distributed over the giant network. We have used the numbers obtained experimentally for the virtual machine configurations, and we have compared our system with a baseline, with a basic cloud system, a commercial cloud system. And the result of the simulation is very promising, because you can see here on the ordinate axis the aggregated bit rate in the network, and here the mean bit rate per link in the network. These curves are relevant to a general cloud network, and the red curves are relevant to the RS system. You can see that we expect a significant advantage for our content distribution network in terms of saving of network resources. So, status of the project. We believe that in 1 or 2 months we have the total system working. We have still to finalize the off-path signaling. 2 of the 3 methods shown before still are in place, already are in place. One is will be completed very soon. We are integrating the optimization function within the CDN Genomic Manager, the brain of our system. It is already almost in place. And we really hope to have some resources from Géant for integrating experiments, Géant resources within our experiments, so as to replicate our simulation within the network, within a Géant network, with the final aim of providing the possibility of extending the Géant service portfolio with some innovative services serving the future medical needs. Well, thank you very much for your attention. Thank you.
Are there any questions from the audience? If not, then probably I will have again one question. Did you consider using dedicated supercomputers, and can you evaluate what is the major difference and what is the benefit of this distributed architecture comparing to a centralized supercomputing architecture?
Well,
of your networks?
Yes, the view of RS is making available genomic processing to most of hospitals in Europe. I mean, supercomputing centers are already in place, and very prestigious research and medical organizations already use them in the US and also in Europe. But the real challenge in the next future is to make this service available to any hospital. And there is also another thing to consider, is that the software implementation by bioinformatics is not currently targeted to supercomputing systems, and sometimes they make not very intelligent use of network resources. So we found more convenient to divide the capacities in slices and manage them through virtual networks dedicated to individual processing needs.
Okay, thank you very much. Any other question?
Yeah.
Yes, the observation that you made about the fact that genomic data is the interest of genomic data, or the relevance of genomic data, doesn't wane or doesn't decay. The popularity doesn't decay as quickly as other kind of data. So that would suggest a different kind of approach in terms of archiving. I was wondering whether you could comment on that difference.
Well, archiving is a real issue, but it is a real issue that very much related to the current status of archiving research for big data. I mean that relational databases is not the best approach for that. We need space, a lot of space, and indexing individual components is done in a sequential way without a lot of relationship within individual components. But what is important is to make suitable forecasts about the amount of data that in a given zone will be made available, and make intelligent caching so as to allow final users to having data quite close. Otherwise, it is the result would be to flood the network with unusable data. I mean, I have also evaluated, other research group have evaluated the possibility to handle this data also using an SEN approach, information-centric networking approach. In this case, we had a major problem for to concern the naming of the contents, because this area is not measured, and sometimes components are addressed in different research centers with various names, even if contents are related to the same thing. And the lack of a standardized way of naming prevents from making use of the current, of latest achievements for information-centric networking. But it is an open issue that a lot of research is currently done on that. I cannot be more precise because it is a real challenge. We are still struggling on that. Welcome.
Thank you again for your presentation. And our last speaker of this session will be Brent Sweeny. He has been working for Internet since ARPANET. He was principal network engineer building of Internet 2 network. He played major role of engineering and operating Internet 2, National Lambda Rail, CIC, Omnipop, and Transpac, and some other prestigious system. He is respected tutor and speaker nationally and internationally on Internet-related technical topics. And he currently presents a quite kind of challenge that a kind of very well-known problem of asymmetrical routing. He tried to propose something to help to resolve that problem.
Sure.
Brent, the floor is yours.
Can you hear me? Do I need to give you a chance to stretch? 5 seconds. Do whatever you need to do. I'll tell you a quick story too, just that's interesting. So I'm from Indiana University in the United States, and sort of a small world thing. The president of Ireland, who is an Indiana University graduate, just spoke at our commencement exercises for our graduates just the beginning of this month. So the president of Ireland has been to Indiana, and I'm here in Ireland. Small world, eh? So the previous presentations have been about issues and networks and projects that are real, that are sort of underway in some way. I'm going to talk about something that's completely unreal, but that addresses, I think, a real problem. And that's what I want to try and get at today. So I'm going to talk about what at least a proposed solution to a way of allowing end sites to direct traffic that is not, I think, possible today. So what are some of the issues? I'll be talking about what's the problem I'm trying to solve, and why this might be a good idea, why this might not be a good idea, and how it might be accomplished, and also talk a little bit about what we've done to show that it could be done this way. So the idea is to allow end sites to influence the direction that their traffic returns to them. Now, there are lots of ways of doing this for neighbors who are very near you. There are not very many good ways of doing this for neighbors who are not near you. There are a number of ways to do this that I call blunt tools that allow you to influence traffic in ways that affect all kinds of other people, but not very many ways that allow you to affect it in a more precise way, particularly for neighbors who are some distance away. So this is kind of a network geeky talk. But the idea is to allow the end site, the one who originates the traffic and to whom the traffic is returning, to request that to some upstream neighbor some distance away, that they send the traffic to you by some particular path. And in the drawing here, let's see, one of these is a pointer. The idea is that here's the end site. There are multiple paths back through some kind of spaghetti of networks, and your provider might choose this path by default for her own reasons, and you'd prefer that the traffic come back by this path instead. And so it's a way of issuing a request for that. I call it a hint because it's not a requirement, but it's something that could be done if it's all the same to you. Please do this. And it uses a well-known BGP community. This isn't about BGP communities, but it uses BGP communities. And it's optional. So why? There might be a number of reasons. One of them is that you may have a 10 gigabit path one way and a 1 gigabit path this way. And the provider may prefer this path for one reason or another, and you'd prefer to take this path. You might be doing some kind of demonstration. You want to distribute traffic across both paths in some way that you direct. You may have reasons, you may want to send it across a congested path on purpose because you have an experiment and you want to test QoS or something like that, or do some kind of demonstration. You may do it for symmetries or to avoid a path that's broken or lossy or some other kind of problem. It allows you to have some control over the path that your traffic might take. We see the kind of need for this often in the International Supercomputing Conference, where we're using lots and lots and lots of different networks and trying to usually manually adjust the way the traffic is engineered across all of these different paths to avoid congestion and other people interfering with each other. And to enable people to do this in some programmatic way could be really, really useful. So I suggest at least that the existing ways of doing this are not really adequate to do it. And I thought that I talked about it in this slide. Here's where I talk about it. Let me go back a little bit more. So part of the idea too is that instead of having a whole bunch of specialized individual solutions, network by network, that we come up, if possible, with some kind of generalized way to do this, or a programmatic way to do this, that might be applied in more than one case. So you're all familiar with the way of using communities to request a particular behavior from an upstream neighbor. Almost all of the carriers now have something like this. So you can use level 3 and some kind of marker to request one thing, and Géant or Internet 2 or someone else to request some other particular behavior. The idea here, again, is to try and use some kind of generalized way of requesting a particular steering mechanism that might be programmatic in some way and might apply to more than one network. And the idea that, you know, the research and education community, at least among ourselves, might be able to agree on some kind of common behavior. We've done the same thing with other kinds of things like jumbo frames and some of our behavior with IPv6 and some other things that we've been able to agree on to make at least the behavior work for us as a community. And it gives us a kind of a critical mass. And that in our community, at least, we tend more to know each other. So it might be possible to make a request to an upstream neighbor, and they may be able to say, well, yeah, I trust the people at the University of Melbourne or the University of Trinity College or something like that. Someone who I, you know, these guys I will allow to make that request and I'll do something about it. Those other people over there I may not allow it. And so it allows people to tune their requests rather than to reject all of them or accept all of them necessarily. So what's wrong with the current alternatives? Some of the existing methods that you can use are MEDS. You know, this is all kind of BGP talk now, but MEDS, which communicates a weight to the first upstream neighbor, but they only go that far. So MEDS give you all sorts of metrics, but they don't go very far. AS prepending is a really, really common way of padding ASs on top of your advertisement to make it less desirable, to make it a longer AS path. But it affects everybody who sees it. And so that's the reason I call that one a blunt tool. You can send more specific advertisements. So you can send a smaller advertisement. So, instead of sending a /16, you send a /24 for this particular prefix, and you send it to one peer but not another. Again, that affects everybody who sees it along the entire upstream path of that advertisement. Some people, instead of sending more specific advertisements, only send some advertisements one way and some advertisements another way, which I call a very blunt tool because it limits the accessibility of your network only to the people who see that particular advertisement. And so what I'm calling here local pref, I call this nudging. There are some ways of using advertisements with particular peers using BGP communities to say, I'd like you to adjust your prefixes this way or that way. But again, that usually only works for the next neighbor. And there are lots of schemes about doing that. But they're only usually per vendor, per carrier, per neighbor. They're not the same almost anywhere. Although some people use similar conventions. Why not do this? Well, there are a number of problems it might cause. The first one I mentioned here, does anybody remember IP source route? If you're old enough, you might remember that. But you know, it's a provision that's built into the IP protocol, and almost, as far as I know, remember, universally discouraged. The idea was that we want to allow the carriers to control how the traffic runs. They're the ones who own that part of the network. They should decide which way they send their traffic, or our traffic. And you know, we shouldn't allow the people downstream to make requests or to control the way the traffic routes. There are all sorts of other security problems and some other things with IP source route. You know, does that end site down there know something about the network topology that I don't know? Should I trust them? Should I honor their request? Should I do something about that? Perhaps they do, as I pointed out in the earlier slide. Perhaps that there's some reason that they have for requesting the traffic go a particular path or not. You know, are we allowing the wrong people to make decisions about traffic engineering? I don't want them to change the way my network flows because I've got it working in a certain way. And you know, how do you know that they're the ones who really requested it? Could it be spoofed in some way? I believe not, but you know, that's one of the questions. You know, does it destabilize your network troubleshooting? Does it make it harder to know what's going on and why? You know, you have it set up in a way that's predictable and understandable. Do you want it to work in a way that you have to look harder to figure out why traffic is behaving in the way it is? Will it scale? Is it maintainable? Is it understandable? Is it documented? And again, I believe that it could be, it's particularly if you're using a scheme that's more generalized. And you know, some people just don't allow BGP communities that aren't theirs to go through, and you know, this may not reach you. I think that if it doesn't reach you, there's no loss. You're not any worse off than you are today, because there's nothing there happening now. So how do I propose to do this? I use an existing method, the BGP community, but I'm using it in a different way. So I'm not doing the usual things we do with BGP communities, but something different. But it's the idea. It's the same idea. So a BGP community, for those of you who may not know what we're talking about, it's a 32-bit or nowadays also a 64-bit value that's commonly encoded in two parts. The first part usually is the AS number of, you know, that's used as kind of a marker. It might be the AS number of the network provider, your upstream provider, the one you're talking to usually. So if your upstream provider is Tata, for instance, or some other carrier, you might put Tata's AS number there. And then the lower part is also 8 bits or 16 bits or some other part of the network that's basically a signal to them that's specific to that particular provider, saying do something that's, you know, part of your scheme that I understand. Do a local pref, send it to somebody else, don't send it to somebody else, you know, mark it in some way. You know, there are all sorts of different kinds of things. Sometimes the lists are very long, as you may know. Sometimes there's only a few. For instance, Internet 2 has a particular way of advertising a prefix that asks you to black hole it because I'm being DDoSed or something like that, and I want that traffic to be thrown away at the top so it doesn't use up part of our kind of precious network bandwidth between the provider and me. So you can use it to mark your traffic in a way that exercises a certain policy that's understood between you and that provider, but usually only you and that provider. Usually transitive, I'm indicated, sometimes they're not. And there are some predefined, well-known community values that are part of the BGP specification. So how do we do this using communities? The idea is to propose for that first part, that's usually the carrier AS, to provide for a single well-known AS number that's unique and that's agreed on and is part of this what I call a protocol. And in the example on this slide, it's 60,000, which is part of the reserved block. But I actually think it's important to have one that's unique. 60,000 can be used by anybody for anything. So in the later slide, I'll show you a solution to that. And you attach a BGP community. It's an attribute of a prefix announcement. So you attach it to the prefix announcement that you send upstream. And the idea here is that you use, whoops, wrong button. You use the well-known AS, and then the AS of the network that you want to have the traffic come back through. So, you know, 3 or 4 or 5 or 6 hops away, my traffic could come back through 2 or 3 different paths back towards me. And I would like to ask you, upstream provider, way up there, way out there, to send my traffic back through AS11537 if you have a choice. AS11537 is Internet 2 in the United States. And as I say here in the language, you know, you can read that kind of request as, please, whoever sees this, when you're deciding which available path to send traffic back to me, I'd prefer you use AS11537. And some networks, you know, it has to get to that provider somehow, and someone has to send it for this to work. And the idea is that you can do it, if you choose to participate, you can do it, you can implement the hint any way you choose, if you choose to do it at all. Some other things that might be done with it are to indicate degrees of preference. I prefer that one most of all, but maybe this one is okay too. Or don't use that one, or something like that. You might have a a source path indicated, a stack of prefixes or something like that. But for the moment, it's very simple, just a single thing. You know, you could mark continental kinds of things or something like that. So again, here's the original diagram with some specifics on it now. So the end site sends up a hint. The upstream network that might be, you know, more than 2 or 3 hops away, could be far away, sees the hint and sends the traffic back this way instead of that way. That's just the basic idea. The end site could change the prefix, the preference anytime, could change the direction it goes, and the upstream network that implements it could change his or her way of responding to it anytime that they wanted to. So it needs general agreement on a method, it needs some willingness at the end user sites and at the provider sites to make it happen. And we've done it, at least shown that it's possible to do. So if I want to honor some hinting requests from some peers, and I have the marking, this is just some, I did it again. Some sample Junos language to very, very simply kind of do something like this, to using local preference to implement it. I allow myself to respond to hints from Internet 2 or from National Lambda Rail in the United States, and those are their 2 ASs, and I can send the traffic back this way or that way, depending on what I want to do. And if nothing else happens, or there's, you know, I don't have other peers, or there's no hint, or I choose not to do it for other networks, then I just don't have a policy for that. Or I use normal BGP path selection. So this is sort of a variation on the other diagram, but here I have my university in Bloomington, and I have a /24 buried away in that campus. And I have some networks that serve me. There's a Gigapop there and a bunch of commodity peers and NLR and Internet 2. And the usual traffic flow for the traffic from Transpac network, which is over between Los Angeles and Tokyo, an international network, normally sends its traffic back this way. But I'd like to send the traffic back through NLR instead. So the university sends this hinting announcement upstream, and it passes through the Indiana Gigapop, and it passes through Internet 2, and it passes also through NLR. The commodity peers may or may not see it and send it on. And Transpac has chosen to implement that particular policy for that particular announcement. And so, whoops, did it again. It modifies its policy to change the return flow, the path that it returns the traffic back towards Indiana University through this other path, just for that one advertisement. And you know, the originating university can turn that on or off however it wants, depending on what its needs are, without requiring any manual special kinds of behavior from Transpac or from Internet 2. And in fact, Internet 2 and the Indiana Gigapop and NLR wouldn't have had to do anything at all to change. They just allow this traffic to pass through. They may have this in place for other kinds of choices that they would make, but not for that one. So the traffic in this case was transparent to Internet 2 and NLR. So we construct the hint. Oh, what are we doing? There's Junos. Oh, here's some Junos code. Must have duplicated something here. So this is a more specific policy about how it was done, and sending it to the next hop. Similar to the other thing. So things to watch out for. One of the major things would be to watch out for loops. You don't want your traffic to, you know, to head back the direction it came from instead of the direction towards you. The sending provider is going to return traffic towards you, but you need to exercise some care to make sure that it doesn't happen and doesn't start any kinds of loops. So you'd have to be careful with multiple hints and things that might confuse the protocol, and it's kind of the same problem with source routing. we've done, so the demonstration, the little thing I showed you there was a real project. We really did that through NLR and Internet2 and Transpac. We have worked with NREN, procured from NREN a unique AS 27198 to use for signaling. It exists and is designated, and it's universally unique. I'd like to get one that I don't have to pay for, so it's more likely to be established for some period of time. But right now we're paying for it. And we have some expressions of interest from RNE networks in the United States. Again, I think that this would be a great option to have for supercomputing in particular, but all sorts of other kind of experimental and production uses, I think. And we've created a mailing list for people who are interested in it. I think one of the things that we need would be for some way for people to indicate, I support this as a provider. Right now, it's, we have a community, we can talk about it. They could put it on a web page as part of their documentation or other kinds of things. Just indicating in the same way, these are the policies I support. They could also indicate that they support this kind of protocol. A bunch of references about BGP communities. One of the interesting ones is a recent talk, well, relatively recent, at NANOG, talking about BGP communities, but what he's really talking about is using BGP communities to steer traffic in innovative ways, and he refers to some of this stuff as well. And I've talked about this at a whole bunch of Internet2 and NLR meetings. And I've been encouraged to write this up as an RFC, which I hope to do when I have more time soon. And thank you. Do you have any questions? Oh, my. Okay.
Thank you. Dave Wilson, HEANet. My first question is, my goodness, where was this 13 years ago when I needed it?
Well, I was talking about it about 8 years ago, but yeah, I've been trying to kind of present it to this group for a long time, so I'm glad I got to.
My real question is, this looks like a great feature for any networks. I can see operationally this will be tremendously useful. It looks like it's something we'd have to configure per AS, per trusted neighbor. Yeah. And I have actually quite a lot of neighbors I'd probably trust. Is there any way we could try and mitigate that complexity?
One thing that helps mitigate the complexity is that you only have to do it once. So you could set up a set of policies that allow it to happen and then just leave them in place, and it's sort of set and forget. But I can't think of a way of generalizing it more, although you might be able to write some language into your policies to do that. I mean, to pick up the AS and send it to that AS. I can't think of a way to do it, to express it in Junos or iOS right now, but I can imagine that it might be possible somehow.
Thank you. Jan Ferry from Dijk in Denmark. I wanted, first of all, why do you stick to the small AS numbers?
Partly because when I first was, we could do it with either one, but when I was first proposing it, the 64-bit ASs were hardly used by anyone, and some of the router vendors didn't support them. Now everybody does, and yeah, we could do that. There's not really any need for it, at least in the simple form that it exists today. If you wanted to attach more features to it, you could.
Well, you need to at least tell which AS number you want to pass through, and
yeah,
that could be
that's exactly true.
32-bit.
Yeah. So that's a good reason to argue for extended AS.
Am I right that along the information you receive as an upstream provider, you have the false AS number saying this is some phony thing.
Yeah.
You have the AS number which you're going to suggest, and then embedded in the BGP packet you have who is sending it. Or is this something that really affects everybody?
You have the originating AS, which is always part of the BGP advertisement.
Okay, so it's
this is a BGP community that's associated with it. But the part you're right about is that, so this could be anything. This could be a 16-bit AS or a 32-bit AS. But the trick is that this one needs to accommodate a 32-bit AS. And I think that was your point, right?
Yes, and the second thing was that it's still a per AES number trick you're doing. It's not a general thing.
Well, it's general in the sense that whoever sends it, if I choose to do that, I would, this is in terms of next top neighbors of that upstream peer.
Yeah, but the upstream provider needs to do something based on your AES number.
Possibly.
So you're not just changing the route for everybody.
Right. If the upstream provider chose to honor requests from some people and not others, then you'd have to have some additional policy that would say, if Indiana University asks me to do it, I'll do it. I'll send it back through Internet 2, which is what that advertisement is. But if the University of Kentucky asked for it, then I won't. Yeah. Yes, that's true.
Okay, thank you very much for your presentation. It was very helpful.
Thank you all.
And some announcements. There will be an opening reception today from 6:30, if I remember well. Probably you won't forget your badge because you are here. It will be on the O'Reilly hall. And fill your evaluation form. That's the other important announcement. And there will be buses only for the main conference hotel after the session, so the opening reception. Thank you very much for your attention, and have a nice evening at the opening reception. Thank you very much.